I want to discuss the stretch that occurs in a cable as a result of it being loaded. So let's take this simple example of a flagpole that is hinged here to the wall at a pivot. We'll call it P. And at the end of the flagpole is a flag, or I represent that by this cylindrical weight. The flagpole itself has got a uniform construction, so you can imagine that its mass, which we'll call little m, acts right in the middle, and the free body diagram for this is capital Mg. Now the tension in the cable is going to be F sub t, and because it's being loaded like this, the cable is going to stretch. So let's call the stretched length, the already stretched length of the cable, we'll call that LC prime. Prime meaning it's already stretched. Let's complete this free body diagram. There's going to be the vertical force and the horizontal force on the hinge. I'm not too concerned with that, with those forces. Let's write the conditions for equilibrium, which is basically Newton's law for rotation and translation. So Newton's law for rotation gives us about the pivot. Remember, the pivot is the point about which we take the torques, because two unknown forces, namely F sub h and F sub v, pass through it. So sum of all the torques about the pivot equals 0. Remember the conventions that we have for torque. Clockwise torques are negative and counterclockwise torques are positive. Gravity here is a clockwise torque because R cross F is into the page and R cross F is into the page for both these forces. Now remember, in the static equilibrium video, we saw another way to find torque, and that is the force times the perpendicular distance of that force from the axis of rotation. The perpendicular distance is this much, and that's L over 2 cosine theta. So that's negative little mg times L over 2 cosine theta, where L is the length of the flagpole. For the weight at the end, it's going to be capital Mg times the entire length cosine theta. And now there's going to be a third contribution from the tension itself. Because of the way I define the angle theta, this angle is also theta. So the torque due to the tension in the cable is R. Now I have not exactly told you what that distance is, so let's do that now. This is attached at the 2/3 L point. In other words, 2/3 of the length from the pivot. That's where the attachment point occurs for the cable. So the torque is given by 2/3 L times the tension force times the angle, sine of the angle between the two, and all that should be equal to 0. So this can be solved. Notice the little l's cancel out, so I can solve this for F sub t. I get F sub t equals m plus m times g cosine theta. Actually, there's m over 2 there, so m over 2 plus m g cosine theta divided by 2/3 sine theta. Now if you remember, sine theta and cosine theta, so cosine over sine is cot, so I can write this as 3/2 little m over 2 plus capital M times g cot theta. So that's our result. Let's just save that equation. And like I said, you can also do sigma fx equals 0, where we can take this coordinate system to be like that, and sigma fy equals 0. Let me just write that down for completion. Those equations will be F sub h equals ft, and here I get all the up forces equal to all the down forces, so F sub v equals m plus mg. So if necessary, we already know the vertical components right there. The horizontal component can be found the moment you find the tension by setting it equal to the horizontal component. So those are not very interesting. So if the problem also asked us to find the pivot force in Cartesian coordinates, you can do that. My chief concern, though, is to figure out the true length of the cable. This is the length after the loading. What was the length before the loading? So let's also write an expression for LC prime. By geometry, LC prime is 2/3 L cosine theta. I'm going to call that equation 2. Now our main purpose of this video is to write LC prime as the original length of the cable plus the stretch in the cable. How do we find the stretch in the cable? That's the subject of elasticity. So here I'm going to give you a little introduction to elasticity, just what I need to finish this problem. It's a big subject. The person's name to remember is Thomas Young. He conducted a series of experiments and he showed that for most substances there is a constant now called Young's modulus. I don't think he called it that himself. The ratio of stress to strain of most materials is a constant. So for example, all aluminum wires or all steel wires have the same Young's modulus Y. The Young's modulus for steel, for reference, is around 200 gigapascals. Of course, there are different kinds of steel like carbon steel and tungsten steel. We're not getting down to the fine details, but on average it's about 200 gigapascals, where giga means 10 to the power 9, and pascals is just newtons per square meter. It's a unit of pressure. Now let's try to understand what stress and strain mean. So just for the sake of simplicity, let's consider a cable that is like that. So when I magnify a cable, it up close looks like that. Most cables in daily life are circular in cross-section. So the cross-sectional area of a cable is got by cutting it somewhere perpendicular to its length, and I'm going to call that cross-sectional area A perpendicular. So stress is defined as whatever force you're applying, in this case it's the force of tension on the cable, divided by the cross-sectional area. You will see that the units here already give us newtons per square meter, because force is measured in newtons and area in square meters. So you already get the Young's modulus units, gigapascals, which means strain must have no units. And indeed it does not, because strain is defined as the change in length divided by the original length. That's the definition of strain. So now let's substitute it all back in this Young's modulus to get the expression that we need to work out this problem. Young's modulus of steel, because I'm going to assume the cable is made of steel, is going to be the force, and let's assume the diameter of the cable is given, d, divided by the area, and area is pi r squared or pi d squared over 4, divided by the strain, which is the change in length over the initial length. Now this I can solve for delta L. Let me do that next. Delta L. So this L naught comes upstairs, and then everything else is down. Of course 4 also goes up. So this is going to be 4 ft L naught over, and when I take delta L over here, I'll bring the ys down here. So that's pi d squared times ys. So that's our expression for the change in length of the cable. Let's actually go about evaluating that change in length. To do that, we need to make an assumption about how thick the cable is. Let me take the diameter of the cable to be 1 millimeter, which is 10 to the minus 3 meters. And let's try to evaluate a few things here first. That angle theta looks almost like 30 degrees, so I'll take that also to be the case. And I've not told you the total length L. Let me say take that to be 1 meter. So this is the numerical part of this problem. I just want to show you how big an effect you're going to get here. Now, just for the sake of fun, let's take the flag to be pretty massive, 100 kg, and the flagpole, because there's an m over 2 there, I'm going to take the flagpole to be 200 kg. So this is really, really heavy for 1 meter object. But I just want to see how much of an effect there is. Let's find out the length of the cable using equation 2. I get LC prime equals 2/3 times L, which is 1 meter, times cosine of 30 degrees, which is √3/2. And I did this before I made the video, so that's 0.58 meters. Let's calculate F sub t next, because that's also something we need to find the stretch. So F sub t will be 3/2. Now fortunately I chose little m to be 200, so 200 over 2 is 100 plus another 100, so that's 200. G I'm just going to take 10 meters per second squared, not too hung up on accuracy here. And cot 30 degrees is cosine 30 over sine 30. Cosine 30 is √3/2, sine 30 is half, so that's √3, which is approximately 1.73. And this is 100 here after cancellation. And this also I worked out prior. So it turns out to be 5.2 kilonewtons. Now I can substitute everything in this formula. So I'll write this as delta L equals, unfortunately I don't know the original length either, but I have the original length here in terms of the true length of the cable. So I can write L naught equals LC prime minus delta L, and I can use that for L naught. So let me do that. Delta L equals 4 ft over pi d squared times, for L times the Young's modulus, times LC prime minus delta L. Let's calculate this quantity here. Just get it out of the way. So 4 ft over pi d squared times the Young's modulus is going to be 4 times 5.2 times 10 to the 3 newtons, which I have from there, divided by pi times the diameter, which is 10 to the minus 3 meters squared. And Young's modulus of steel is 200 gigapascals, which I can write as 2 times 10 to the 11, because 200 times 10 to the 9 is the same as 2 times 10 to the 11 pascals. So let's work this out. This actually turns out to be 0.03. There are no units because I get newtons per meter squared, which is the same as pascals, so it's unitless. And it better be unitless because change in length is, there's already a unit of meters here, there's a unit of meters there, so this had better be unitless. Now we are ready to calculate what we need. Delta L is equal to 0.03 times LC prime minus delta L. So you have delta L in both places. However, this is just a linear equation, so it can easily be solved. That's 1 times delta L, and that's 0.03 times delta L with a negative sign. So when I bring it over here, I'm going to get 1.03 times delta L is equal to 0.03 times LC prime. Let's calculate now what delta L is. So delta L is going to be 0.03 divided by 1.03 LC prime. Well, 0.03 over 1.03 is almost 0.03 again. So that's 0.03 times LC prime, which is that, 0.58 meters. And that turns out to be 0.018 meters. Pretty small, but if you write it in millimeters, it's 18 millimeters. That's almost exactly the size of this underline. So the cable does stretch by that much. However, you should imagine the cable is being loaded by something like the weight of 3 sumo wrestlers, I guess. Really heavy people. So it's pretty good stretch for a steel cable, 1 millimeter in diameter. And so the true length of the cable can be found by subtracting. The true length of the cable you need to use for the situation can be found by subtracting this from the actual length of the cable. So the true length will be .58 minus 0.018 or 0.562 meters. So that's the answer to our puzzle.